Okay. All right. So we stopped off yesterday talking about gauge fields, and we set up the dictionary in Euclidean AdS between fields and in the bulk and corresponding operators in conformal representations on the boundary. What I want to do today is start a little bit with telling you a little bit about the Lorentzian context, switch gears to talking about gravity, and then talk about excited states and more gravitational stuff to do with thermal physics. Okay, so what we saw yesterday was that if we look at a scalar field, for example, then, and if you look at the solution near the boundary, it has two independent modes, one which both are power law fall-offs with different powers, which I'd call delta plus and delta minus, which I remind you are given by these expressions in terms of the mass of the scalar and the conformal and the dimension of the space-time. And what we noticed, what I generally argued, was that in general, for outside of a certain range of masses, this mode is not normalizable because this is the slow fall-off mode, whereas this mode is the fast fall-off mode and is normalizable with respect to the Klein-Gordon inner product. Now, in Euclidean space, since space, as I said, is topologically a ball, requiring regularity at the interior of the space-time requires that you have to have the solution, this mode turned on. And so what you need to do is prescribe what value this mode takes, what value this coefficient j of x takes, and that we call the source of the dual operator. It just so happens that in Lorentzian signature, if you now ask the same question, the fall-offs are the same because these just refer to the radial fall-offs, as Stefano was trying to point out. There doesn't seem to be a distinction between Euclidean and Lorentzian at this level. The trouble is that in Lorentz signature, smoothness conditions in the interior of the space-time are different, and it's possible to have a solution that's purely supported by the slow fall-off mode, by the fast fall-off mode. Okay, but by the term that falls off as z to the delta plus. Now, I just wrote the z to the delta minus solution here. If you think of this as a second order ordinary differential equation, there are two linearly independent solutions which start off as z to the delta minus and z to the delta plus, and then you fix those coefficients, and the remaining coefficients here are determined in terms of, so the coefficients here are determined in terms of j of x, and the coefficients here are determined in terms of O. Okay. Now, you could say, why don't I just fix J and O independently, and the solution is well described in terms of by giving both initial conditions and derivatives of initial conditions at the boundary. Well, that would be fine, except that such a solution may not be guaranteed to be smooth. Okay, so we should understand what O, this coefficient O of the z to the delta plus means, given we turn on a source J for the mode that goes like z to the delta minus. And the way to think about it is to actually realize that when you turn on a source for the scalar field and require some interior smoothness conditions, then this coefficient gets determined by the interior boundary condition. And what you should view this coefficient as, you should view this as the response of the scalar to turning on a source. In other words, what they should give you is the expectation value of the dual operator in the presence of the source. So it's like a polarization effect. You turn on a source for the scalar, the corresponding operator polarizes and picks up a wave. Because what we've done in the field theory is we've said we've taken e to the I as CFT, and then we've added a term which is j times O ddx. And if I keep j non-zero, then, and I try to compute the expectation value of O in the presence of j, I would actually do the functional integral over the CFT fields. And normalize, let's say, by the partition function. And if you just walk through the calculation, you'll find that the WEV in the presence of the source is actually given by an integral transform of the source, with the kernel being exactly the 2-point function of the dual operator. Okay, with normalizations factors are fixed here from the explicit solution for scalar fields. I'll use this story again, and I wanted to bring this up because I'll say something more about what another distinction between you. I'll give you an explicit example of a distinction between the Euclidean and Lorentzian solutions in a moment. Okay, but I'll now start using the language where I say that the mode that falls off slowly, which is the non-normalizable mode, I'll call the source, and the mode that falls off fast, I'll call the WEV. And this discussion is very well exemplified if we do the following. If instead of talking about scalar fields, we ask the question, let's turn on a non-trivial metric on the boundary. Let's take our quantum field theory, our boundary conformal field theory, and put it on a background with non-trivial metric gamma mu. So I have my usual AdS spacetime. And what I'm doing is I'm telling you to prescribe a metric for me on this topology on the boundary manifold. And now I'm going to ask, what is the dual geometry and what's happening to the field theory on this curved spacetime? I'll switch back and forth now between Euclidean and Lorentzian signatures. So gamma, for now, you could imagine is a Lorentz signature manifold because the boundary is time-like. Or if you were doing Euclidean, then this is just a Riemannian manifold, Riemannian metric. So specifying gamma on the boundary, I claim, is tantamount to specifying Dirichlet boundary conditions for the gravitons in the bulk for gravitational fields. And these are the only boundary conditions that are allowed for gravitons. So for vector fields, I gave you there are some exceptions. As far as I know, there are no exceptions for gravitons. Now, like the gauge theory, the bulk gravitational theory, there's a bulk gravitational metric, GAB, that needs to be determined with boundary conditions that as I go to the boundary, the metric becomes, we'll see how the metric becomes gamma in a second. But if I again continue to think of evolving inward from the boundary, let's say in some radial coordinate, then I still have to take into account the fact that the gravitational theory has diffeomorphisms, and I need to worry about the diffeomorphism constraints coming from the gravitational dynamics. What would they do if I'm evolving radially inward? Then they would give me radial ADM constraints. Okay, just as usual ADM formulation of Einstein's equations, Hamiltonian formulation of Einstein's equations for time evolution, they would prescribe initial conditions on a space-like slice, and then you would evolve forward. Now, we are trying to prescribe boundary conditions on a time-like slice and evolve along a radial direction. Okay, so evolve in quotes. But as far as the constraint equations are concerned, you can just derive them the same way up to some signs. Okay? Just that the normal to the time-like surface is space-like. And there are two sets of constraints. One, which is the usual constraint coming from in ADM language, the shift vector, and the other which comes from in the ADM language from the lapse function. The radial momentum constraint coming from evolving which is basically you should think of as the Einstein's equations with one leg along the radial direction and one leg along the boundary, tells you that the boundary CFT energy momentum tensor is conserved. So just as current conservation came from radial Gauss law, the boundary energy momentum conservation is a statement of Einstein's equation. It's a constraint equation from the Einstein gravitational dynamics. But gravitational dynamics also has a scalar constraint, the Hamiltonian constraint. And that basically, in this context, tells you that the boundary energy momentum tensor is traceless to leading order. Okay. It won't be traceless if I turn on a non-trivial metric, and we'll see that there's a Weil anomaly. But this statement of the anomaly and the nature of the tracelessness in flat space is a statement that comes from the radial Hamiltonian constraint. So let's see how we would set up the problem for gravitational dynamics by writing down the action and understanding what the way boundary comes up and what this boundary energy momentum tensor is. So I'll take the gravitational dynamics, as I said, in my sequence of steps. I'll take it to be the Einstein-Hilbert dynamics plus a boundary term plus counter terms. And I'll discuss the counter terms in a while. I won't discuss them just yet.
Can I ask a question?
Certainly.
Okay, if you don't fix the Dirichlet boundary conditions, but you fix instead Neumann boundary conditions, and so you have a dynamic boundary, can you say anything about the energy tensor of the energy stress tensor of the theory on that surface? Or not? Well, like, you as an analogous of this relationship if you impose Neumann boundary conditions instead?
Yeah. So let's just ask what would happen if we do that. If we do that, then what would we have to do? We'd have to make the boundary metric dynamical, which means we integrate over the boundary metric, which means we'd have to impose boundary Einstein's equations. Einstein's equations with respect to this gamma. Okay. But what does Einstein's equation tell you? It tells you that the net energy, which is the Einstein tensor, is 0. So you'd be forced to study solutions where the there's no energy momentum tensor, but the energy momentum tensor is completely gauged. Okay. Now, so in principle, this sounds like a plausible statement. And you might say, okay, why can't I impose this boundary condition and study dynamical boundaries? In practice, what I know is if you try to impose this boundary condition, then you don't get a phase space with positive definite inner product. Okay, what that means is that you don't have a unitary theory on the boundary if you impose Neumann boundary conditions for gravity. Okay, so people have tried analyzing these boundary conditions, and there was tentative conclusion that yes, you could perhaps impose Neumann boundary conditions, but a closer examination suggests that it's like trying to impose Neumann boundary conditions for scalars outside the window where you're allowed to impose them. And that violates unitarity bounds. Maybe a better way to say it is the following. See, conservation equations mean that from an operator point of view, T mu is a special operator in the conformal field theory. It sits on the unitarity bound. Its dimension actually is D, exactly determined by unitarity for a spin 2 massless, for a spin 2 operator. So if you try to do something funny to it, you're in danger of violating unitarity. And I think that's what happens. So I don't think that, at least I don't know of a sensible framework where I know how to keep the boundary dynamical and study holographic systems.
Thank you very much.
So coming back to the action, so I have scaled out the G Newton out front into the gravitational action. So I have the Einstein-Hilbert action, and I've normalized my cosmological constant suitably. But there's an important boundary term, okay? Which is the Gibbons-Hawking term, which is the extrinsic curvature integrated on the boundary. So K is extrinsic curvature evaluated with the outward-facing normal. So it's a normal face pointing out of the boundary, it's pointing this way. And I'll just point out that there are various sign problems in most of literature, depending on who's written the paper, because people have written papers in 2 different coordinates. one with the z coordinate I was using yesterday, and a radial coordinate r, which is 1 over z, and the normals point in opposite directions because d by dr points opposite to d by dz. D by dr points in the direction of increasing r, d by dz points in the direction of increasing z, but increasing z is this way and increasing r is that way. So just be careful when you try to compute, because with my the conventions I like are ones where there's an outward pointing normal, and with that convention, this action is what I call the Einstein-Hilbert action, because this action guarantees that the second order Ricci tensor, Ricci scalar, upon variation cancels against the boundary term coming from the extrinsic curvature and gives you the correct Einstein's equations. This discussion you can find, for example, in I believe Appendix C of Wald, for why you need the Gibbons-Hawking boundary term to get the Einstein's equations from the Einstein-Hilbert action. I'll come back to the counter terms, as I said, in a bit. But given the Gibbons-Hawking term, boundary term, and the counter terms, you can define the boundary energy momentum tensor as the variation of this part of the action with respect to the boundary metric. So I can just define T mu nu to be the variation of boundary action plus counter term with respect to the boundary metric up to factors of maybe 2. Want to be consistent with usual discussions. And here's the final expression. So the variation of the variation of the Gibbons-Hawking term of this guy gives you the Brown-York stress tensor, the quasi-local stress tensor of Brown and York, which is just purely determined geometrically in terms of the extrinsic curvature. It's just these two terms. And then the counter term contribution gives you this. And I'll explain where these two terms comes from when I write down the counter term action. The counter term is built out of the metric gamma and its connection. Okay, so it's not built out of anything else. So when I write down the contribution of the counter terms to the boundary stress tensor, there's a piece involving gamma, and there's a piece involving the Einstein tensor of gamma. So when I put these northwest superscripts, the northwest superscripts refer to the gamma refers to the quantities computed for the metric gamma on the boundary. Okay. Let me pause here to make to check that people are happy with this discussion. And this boundary term is really enforcing Dirichlet boundary conditions for bulk gravitons.
So it looks like the counter terms are only on the boundary. Are there no counter terms in the bulk?
The bulk, no, there are no bulk counter terms. So the way I think about the whole discussion is the following: you have a bulk action, which is there to give you a variational principle, okay, which is supposed to give, upon variation, supposed to give you equations of motion. So in this case, it's supposed to give us Einstein's equations with a negative cosmological constant. But usually the variational principle classically is not meaningful unless you tell me the right boundary conditions. And enforcing those boundary conditions, especially if you have an action where the action is not a square of first order terms, but has second order derivatives, it means that usually you need boundary terms. So this term is there to enforce that these two terms, as such, upon variation, give you Einstein's equations and no boundary terms. Okay, so setting delta GAB equals 0 on the boundary implies with Einstein's equations in the bulk. The counter terms are there because this Brown-York stress tensor, this contribution, is by itself divergent and needs regulating. But like in field theory, that regulating business is a question of local counter terms that you add to get finite physical answers with a rigid cutoff. Okay. So what we and so that when you take the cutoff, so you basically have some scheme where you say you have some cutoff, you compute on the cutoff surface, but you want finite answers as you take the cutoff away. So you need to add counter terms to regulate the answer. So they have to be built purely out of boundary data because you can't build them out of bulk data. They're sort of there in field theory terms. And in this case, they're nice because they're purely geometric gadgets. They're completely built out of geometric data on the boundary. And I'll write the action for the counter terms, and you'll see where these two terms come from when I show you the action.
Okay, thank you.
Hi, another question. Is this whole discussion works for both Lorentzian and Euclidean signatures, or is this specific for, is there anything specific here for one type of signature?
No. This discussion of both the boundary terms and the counter terms is universal up to science.
Mm-hmm. Don't you have to also define like initial data if it's Lorentzian signature? But
so again, indeed, I would have to. So if you were trying to do a boundary initial value problem where you were trying to set up initial conditions
mm-hmm.
and evolve, then you also have to tell me what's happening here. As we said the other day, this is
mm-hmm.
not a globally hyperbolic space-time. So it's not enough for you to give me data on this surface, but you also have to tell me what's happening for all time above that surface on the boundary, right?
Mm-hmm.
Now I'm saying, I'm for now not doing that problem. I'm pretending I'm doing radial evolution inside.
Okay, and is that a well-posed problem mathematically?
No, it's not, okay. Because you see, it's not a well-posed problem mathematically because it's not a Cauchy problem, right?
Mm-hmm.
I'm prescribing data on a time-like surface and trying to evolve radially inward. And I'm just for now using this as a proxy to show you some general statements about where these terms come from.
Yeah. Okay. That's fair.
But if you want to come, but once you set up initial conditions, once you set up the initial value problem, you would still want to compute things with this action.
Yeah.
Okay. So for that purposes, this is sufficient. But indeed, we're not talking about the initial value problem just yet.
Okay. Thank you.
Okay. So in vein of Joa's question, let me argue that for purpose of analyzing what the counter terms are and what I need to do, it's sufficient for me to analyze the behavior in some open neighborhood of the boundary. I don't need to analyze what's happening in the interior. Just as for the scalar problem, it was sufficient to know what the fall-offs were, that they were, the fall-offs were z to the delta plus and delta minus. So this calculation is nice to do if we gauge fix. So let me do this by fixing to something that you'll find quite extensively in literature, to the Pfefferman-Graham gauge, where I take my metric in the bulk to be in the following form. So I have chosen to switch off. I'm working in the z coordinates. So my metric is dz squared over z squared plus some boundary metric along the boundary directions g mu nu, which is a function of z and x, and I've scaled out a factor of z squared. And I have decided to set the Pfefferman-Graham gauge is basically set gzz to 1 over z squared, and it sets z mu to 0. So this is like setting the shift to 0 and keeping the lapse to some particular value in usual ADM formulation. You think of the radial ADM formulation. And I'll try to solve for this function g mu nu in a Taylor series in powers of z. Okay. With the boundary condition that g mu nu at z equals 0 is gamma mu nu. So this is where the entry point is. This is my Dirichlet boundary condition. And then everything here should then be determined in terms of that data. We'll see what is determined and what is not. So you can plug in these ansatz into Einstein's equations, which for us are RAB plus D GAB equals 0. And solve them order by order in powers of Z. You'll find that G2 is determined in terms of gamma, G4 is determined in terms of G2 and gamma, and so on and so forth, all the way up to a power of Z that depends on the space-time dimension. The powers go in steps of 2, at least with this coordinatization, and the answers depend on whether the space-time dimension is even or odd. And you'll see why in a second, because the parity of the space-time dimension will be important for anomaly purposes. So if the CFT space-time dimension is odd, then you will find an ambiguity in this expansion, i.e., you'll find a normalizable mode that you cannot fix from gamma information at order Z to the D. Okay, so remember Einstein's equations are second order partial differential equations. If you went back to our scalar, we saw there were two linearly independent fallouts. The statement for Einstein's equations is there are two linearly independent fallouts. Once I've stripped off, whoops, this is going somewhere else. Sorry. Once I strip off a factor of Z squared, the falloffs are at order 1 and at order Z to the D. Stay. Good. So the falloffs are here and here. And in odd space-time dimension, this piece of data is undetermined. It's not determined by gamma. It needs to be determined by some other boundary condition. And remember, again, I'm only doing a near boundary analysis. So I could try fixing this at will, but that doesn't guarantee me anything because then the solution in the interior may be singular. Okay. I have to tune gamma. I have to tune T mu nu subject to what gamma is to ensure that I have a smooth solution in the interior, if I want a smooth solution in the interior. But from a differential equation point of view, gamma mu nu and T mu nu are independent pieces of data I can supply in D odd. In even space-time dimensions, it's almost the same, except that there are two independent coefficients at powers with coming with power Z to the D. One multiplies just Z to the D, but there's also a logarithmic violation of that scaling, which is this coefficient G mu D. This guy is completely fixed by gamma, and T tilde is left unfixed. T tilde has the same setting as T. I didn't write down expressions for the powers G mu nu 4 and so on, but G mu nu at second order, the coefficient of Z squared, has a simple expression in terms of the Ricci tensor of gamma and the Ricci scalar of gamma. So this is some Schouten tensor of this metric gamma mu nu. So this ambiguity that you have at Z to the D is natural because we've only prescribed one boundary condition for a second order differential equation. We've only said what happens to the boundary value of the field. We haven't said what happens to its derivative or some other regularity condition. So we need to prescribe this T mu nu or T mu nu tilde in even dimensions. Okay, so now let me tell you the two cases in turn. And let's focus on the odd dimensions first. In odd dimensions, Einstein's equations tell you that this arbitrary tensor T mu nu is conserved with respect to gamma and traceless. Okay, so it's not fully arbitrary data. It satisfies some constraints with respect to gamma. And if you ask what it is, it's a conserved traceless tensor. So it satisfies the constraint equation. So it is the boundary stress tensor. And you can identify it with the boundary stress tensor up to a dimension dependent coefficient and the central charge. What should we think of T mu nu to be? How should we think of this T mu nu? In the language of what I've used for the scalar, this guy, T mu nu on curved background, is a 1-point function, is really the wave in the presence of the source gamma. If I take a quantum field and put it on a curved background, it will polarize in the vacuum, in the corresponding vacuum state, and that polarization effect will be seen in the fact that the stress, you will get a non-trivial stress energy tensor. The stress energy tensor will pick up a wave. That wave is exactly this guy. I'm just not writing waves anymore in general, but it's in analogy is a 1-point function in the presence of a source gamma. How should we find it? Well, we should find it by asking that we have a good state. And that good state requires me to say that in the interior, I should have a smooth geometry. Stefano, you had a question.
Yeah, just a question if the wave of T mu nu is a bulk wave. So the bulk stress energy tensor requires a wave that sources the Einstein equations?
No, it's a wave of the boundary stress energy tensor viewed as an operator of the boundary CFT.
So that does not back react on the bulk?
It does not back react on the bulk, no.
Okay, thank you. Also, one more question. You said T mu nu must be specified, and you wrote down a relationship between large T mu nu and small T mu nu.
Yes.
How does that specify the, what is it left to specify at this point?
Okay. From the near boundary analysis, which is what I'm doing here, I'm only trying to solve the equations in the neighborhood of the boundary. So I have Z going this way, and I'm solving equations somewhere here in some open neighborhood of the boundary. In fact, this expansion has zero radius of convergence. But what do you know what's happening far away? Okay. So you might want a smooth spacetime. That's a second boundary condition for Einstein's equations. If you say that you have a smooth spacetime, then given a gamma, the smoothness condition gives you a second boundary condition that pins down what this normalizable piece you have to add is. Just like with our scalar problem, it wasn't like it wasn't that the scalar wave was, we could have said it's arbitrary data from the boundary expansion point of view, but it's a physical condition that we want that wave to be the correct wave for the scalar field, scalar operator in the appropriate state. And here I'm just studying quantum field theory in a curved spacetime. I should get a wave because the vacuum polarizes, but the statement I want to say that the correct vacuum geometry is a smooth bulk geometry. Okay. Now, going back to your previous question, I did switch off for this discussion bulk matter. I didn't put any matter, I just wrote down gravitational degrees of freedom in this action. I can add matter here, that's okay. And then what I would do is I would then solve for Einstein's equations with matter on this side. Let me use a different font for the bulk matter. T matter AB. Okay, plus matter equations of motion. this bulk matter will definitely back react on the geometry. But that would just tell you that there are other waves in addition to the stress tensor wave on the boundary, because the matter equation will also source the matter field. And that matter field will also have appropriate fall-offs at the boundary, which you will use to read off its waves. So I was going to sort of split the discussion up, but since you asked, indeed, if I just turn on boundary metric, I would get waves for the energy momentum tensor. But if you turn on other operators as well, you get waves for those guys as well. And you can write down geometries where all of these are allowed. But you have to solve these equations.
Just
Go ahead,
following up on that answer, this is from the bulk perspective. What you're doing is you're solving Einstein's equations near the boundary, and you're trying to fix what are the coefficients such that thinking that at some point you'd actually want to solve the full boundary, the full Einstein's equations in the full bulk.
Correct.
And then you interpreting that little t mu nu as big T mu nu from the boundary, that's just an interpretation from the CFT dictionary. It's not actually data that will tell you what little t mu nu is.
Correct. Exactly. Yes. So little t mu nu and big T mu nu, which are just related by us up in this language by coefficient, the central charge and dimension, they are determined by Einstein's equations and smoothness of the bulk geometry. They're not data you get to prescribe.
What's the interpretation of determining the little t mu nu in terms of IR smoothness? What does IR smoothness mean in the CFT?
So what it means is the following. Suppose we think of quantum field theory in some quantum fields in curved spacetime. Now, what do we mean by the vacuum in the curved spacetime? We need some kind of state. If you do canonical quantization, you want to define creation and annihilation operators and say that you're sort of, with respect to that state, all the annihilation operators annihilate that state. But we know famously that in curved spacetime, that vacuum can be polarized. So there can be non-trivial expectation value of energy, the energy operator, defined with respect to your new creation and annihilation operators on this curved spacetime. So in other words, let's think of just Casimir energies, for example. You can have Casimir energies if you take a vacuum on a curved space. We need to get that Casimir energy from somewhere. That's what I call vacuum polarization. Now, in perturbative field theory, you would get that by saying exactly what I said. Annihilation operators annihilate the vacuum. In gravity, I'm saying that condition is equivalent to putting smoothness. Now, I haven't proved this to you. It's a good guess. And this is sort of one of the bigger open questions. How do you actually understand? I mean, this will tie back to other questions that Stefano asked. For example, how do you reconstruct geometry? How do you know that the state I constructed in the field theory is the correct vacuum state for field theory on that curved background? So the way we know this is by checking in examples and seeing that the results we get are not inconsistent. And I'll show you some examples as we go.
Okay, that was very clear. Thank you.
So I focused on the odd spacetime boundary dimension because then there's only one piece of data and it's very clean. That guy is the polarization data of the stress coming from the vacuum polarizing on curved manifold. In even boundary dimensions, I told you that we have two pieces. We naively seem to have two pieces of data, one corresponding to the power z to the d, and the other corresponding to the power z to the d log z. The coefficient of the log is completely determined as some functional of gamma. Okay, and it's traceless and conserved with respect to gamma. So it behaves like a stress tensor, but it's not the stress tensor, as you'll see. This t tilde piece, the coefficient of z to the d, is not determined. It's the analog of T mu nu, which is why I use the same notation. And you can split it into some known functional of gamma plus some analog of T mu nu. Okay. The reason I split it is because this guy has a determined divergence and a determined trace. And if I split off the piece, I can make sure that this T mu nu is divergence free, but the price I pay is it's not trace free. Okay. So in other words, in even dimensions, there's a part of the boundary data that is conserved, but not traceless. But that makes perfect sense because in even dimensional theories, you can have a trace anomaly coming from vacuum polarization. So let's say we're doing two-dimensional CFTs. A two-dimensional CFT, when you study it on the plane, it has a vacuum state, which you can say is the BPZ vacuum annihilated by the Virasoro generators Ln with n greater than -1. Sorry, n greater than 1, and it also is annihilated by L-1, and it has some 0 point. Vacuum is definitely annihilated by everything with L greater than -1. Sorry. But if you put it on a curved background, like a sphere, then the stress tensor is not traceless. It picks up a conformal anomaly term, which is proportional to the boundary background Ricci curvature, with a coefficient that's determined by the central charge. Okay, this is just if you put the conformal field on a two sphere, this is just totally vacuum polarization. It's a Casimir energy on the two sphere coming from this in this case. And the structure of the traces that you get here is precisely the structure of the traces that you get from conformal field theory. You get exactly the Weil anomaly coefficients. In two dimensions, you get C over 24 pi times the boundary curvature of the metric with of the space with metric gamma, and the central charge in AdS3 is related to the. I used the definition before of C effective to be L AdS to the d-1 over 16 pi g Newton. But long before AdS CFT, Brown and Heno had argued that in AdS3, you have a boundary Virasoro symmetry with a central charge that's not quite that normalization, but slightly different normalization of by factor of 12 pi. And I just wrote this answer more in a CFT language because this is much nicer. If you compute this for n equals 4 super-Young mills, for example, you get the n equals 4 central charge n squared times. So now in 4 dimensions, there's also a conformal anomaly, except that the conformal anomaly is a sum of 2 pieces. One which comes from the Euler character, the Gauss Bonnet term, and one which comes from some particular contraction of the Weil tensor. There are 2 independent coefficients, which are usually called A and C. It just so happens that in the supergravity limit, these 2 coefficients are the same, and that's why you get a sum of E4 plus I4. If you go to 6 dimensions, there's a 6-dimensional Euler character, which is the A Weil anomaly, and there are 3 independent Weil contractions, which give you 3 independent coefficients at 6th order. 3 or 2, I forget, but all of those you can get direct. You can get a linear combination of those in supergravity from this Weil anomaly analysis. So this anomaly discussion is parallel to the anomaly discussion I said for Chern-Simons-Toft anomalies. It's just now I'm just not talking about it. I'm talking about the boundary conformal anomaly coming from scale invariance violation. Questions?
Are these 3 parameters that you mentioned in 60, are they related to the A theorems?
the coefficient of this guy is related to the A theorem. So yes, the coefficient of the Euler character in general dimensions is related to the A theorem. It just so happens that in 2 dimensions, the coefficient of the Euler character, which is R, is called C. Yeah, so indeed, so there is a holographic, people have tried analyzing how to separate these 2 coefficients by having higher derivative terms, trying to see whether the A theorem gives you constraints on higher derivative terms, and so on and so forth. But I'll not try to get into that discussion, because if you had a higher derivative terms to the gravitational action, you will get changes here. You'll get other boundary terms, which will change the anomaly coefficients.
Now, what happens if you turn on other source on the boundary, like for other fields?
If I turn on other fields, give me 2 minutes. I'll address that. I'll say something about other fields in 2 minutes. And all of this, by the way, I didn't really solve Einstein's equations. Okay, I only solved them in the near boundary expansion. So I have to do a bit more to actually solve the equations in the near boundary expansion. Sergio, I'll answer your question after the talk if someone hasn't answered it by then. But you can analyze from this near boundary expansion the divergences that you get from these fall-offs, from the z to the z squared, z to the 4, and so on. And one can try to write down, like we did for the scalar field, a counter terms, the counter terms that would give you what so that you can compute finite stress tensors. And I'll just write that down. I won't go through the exercise. You just analyze fall-offs and divergences. And the counter terms are organized as follows. They're organized as boundary data. Sorry, there's a root G here. They're organized as boundary data, pure boundary terms, which are functionals of the boundary metric gamma, purely gravitational counter terms. So you can add a boundary cosmological constant. You can add a boundary Einstein-Hilbert term. You can add a boundary higher derivative term, and so on and so forth. And I just organize again, like I did for the scalar, the whole thing in terms of powers of in some effective field theory derivative counting parameter. Depending on which dimension you're in, what you're computing, you only need a finite number of them, so I don't need to continue this ad infinitum. The coefficients here are fixed by divergence analysis of how things blow up as I go to the boundary. I'll just point out that you can actually eyeball these coefficients and see in which dimensions you have anomalies. These coefficients they are 1 over d minus 2 and 1 over d minus 4. In dim reg will become logs in the neighborhood of 2 dimensions and 4 dimensions, and these are precisely the conformal anomaly terms. So this 4 derivative term is really some combination of E4 and I4, which is really giving you the Weil anomaly in 4 dimensions. This really is the Weil anomaly in 2 dimensions, so forth. Okay. And now, so now let me answer one question, and then we can come to Zhengdi's question. If you try to solve Einstein's equations, pure gravitational solutions, solve them, compute the on-shell value of this of the action, and vary with respect to the boundary metric, you get the stress tensor. This term can be integrated away by parts, because this will have Einstein's equations will kill part of this. This term will cancel with part of the variation from here. But really, all the action is somewhere here. And I write all these terms down because later when I compute things like the Gibbons-Hawking free energy, I will need to keep these terms if I want to actually compute the free energy from gravity. Okay. Questions? Okay, so now let's address this question of how we could excite the state. And I'll take an example to illustrate what I was asked. Let's try to look at a class of excited states using the state operator correspondence in the CFT. Suppose I have an operator of some dimension delta and some spin indices. I can act on it with a vacuum and create a state. From CFT point of view, if I try to compute the energy, which I will use, which by this Hamiltonian, I mean the dilatation generator, I'll actually pull out the dilatation charge of this operator. In fact, I'll just pull out its conformal dimension. If I act with one operator, I'll be creating a single particle excitation. And I told you that in global AdS, the single particle excitations, depending on the operator, they have energy delta, and then they have harmonics on top of it. L is the angular momentum quantum number, and N is the radial harmonic. Now, if I add a few particles, nothing is going to happen because a few particle state can't change the geometry, because the energy in a few particle states, say E, is not enough to have an order 1 correction to the geometry. To have an order 1 correction to the geometry, I need the energy in units of the Newton's constant to be order 1. But Newton's constant is order 1 over C effective. So I need energies of order C effective to have a non-trivial geometry. So I have to build heavily coherent states of many particle excitations to actually get somewhere. So in most discussions, you'll see that people will talk about heavy states, and the heavy states are states whose energy scales like C effective, because those are the only states that change the geometry away from being pure AdS in a non-trivial fashion. When I talked about vacuum polarization, I was implicitly doing that because by changing the boundary conditions, I was constructing a state whose energy momentum tends to scale like C effective. Because my coefficient here was, if T was order 1 from the bulk, then T mu nu in the boundary is order C effective, which is basically the 1-point function of the Hamiltonian operator. So let's take an example that will address Jengdi's question. Let's take a scalar field. Let's take the Einstein scalar problem. So let's take the bulk action to be the Einstein-Hilbert term plus cosmological constant. Let me write equations of motion. So I'll write RAB plus DGAB is the energy momentum tensor of a scalar field. And I'll write the Klein-Gordon equation for scale.
Could you repeat your statement about heavy state, please?
Yeah. So I'm saying that in order for a state to have a geometry that's appreciable, that is different from the AdS geometry, that state needs to have an energy of order 1 of order C effective. If the energy is not order C effective, then in gravitational parlance, I don't have enough energy to back react. So single particle state or few particle states or even order square root C effective particle states don't do the job. I actually need to put macroscopic amount of excitations of order C effective to get something non-trivial. So in other words, you could imagine a few graviton states in the bulk. just few gravitons sloshing around in the AdS spacetime. It's obtained by acting with a multi-trace operator of many copies of stress tensor on the boundary, but the geometry is just AdS.
Okay, so you're saying that the central charge scales with n squared, and so it's a very large number, and so you need a lot of fields in order to decide a lot of fields in order to obtain modification of AdS.
Or I need to make a coherent state of a single field, a very highly excited coherent state of a single field to make a geometry which is very different. Yes.
That makes sense. Thank you.
So I can try to solve these equations for Einstein scalar problem. And let me try to populate the scale. Let's do this in global AdS. And let me just try to populate the scalar in the lowest harmonic in the state with energy delta. And as I said, but scalar, so I can coherently put many scalars in that ground state, like make a Bose-Einstein condensate of those scalars. Well, if I put the scalar in that ground state, then phi, the solution for the scalar, now in Lorentz signature as a function of time, the radial coordinate and angles. Let me not ignore the angles. Let me make it spherically symmetric. Will be proportional to e to the minus I omega t times some profile function phi for the scalar. But the stress tensor will be such that it will come with contributions from a mode with positive energy and a mode with negative energy, and it will be function purely of the radial coordinate alone, of this profile function alone. So you could find a static geometry where the scalar is sloshing around, in fact, just oscillating around in the bulk, but the scalar just sloshes around, oscillates in time, but the corresponding wave function phi of r in turn tells you what the metric function is. So there's some scale, and I'll take the metric to be some g of r dt squared plus dr squared over h of r plus r squared d omega squared. And we can write this down. You can write down solutions where g, h, and phi are determined from these two equations. What would we get? We'd get some solution where there's a wave for the scalar, because we have a coherent state of the scalars. So in that coherent state, if I try to compute the scalar operator expectation value, I'll get a non-zero answer. Okay, but I'll also get a state with non-zero energy density, because this is back reacting and it's going to give me a new geometry. So this would look qualitatively, up to the fact that the scalar is not actually static, but it's oscillating like a star. It's a scalar condensate, which has non-trivial one-point functions for both the scalar operator and the energy momentum tensor. You could do this for other fields. You could do this for fermions. You could actually try to build a star. You could try to build an analog of a neutron star in AdS by putting finite density fermions and asking how are they gravitationally bound together, not just, and there's a slight difference from flat space, because now the cosmological constant is also pulling things down towards the center of AdS. So the gravitationally, the Newtonian force towards the center of AdS is stronger, in a sense of speaking, than in flat space. But nevertheless, such stars exist, and people have tried constructing them. And you can study them as non-trivial states in the boundary field theory. But all of these will now depend very much on how we set up the problem, what fields we turn on, what operators we turn on. And some of them will have smooth geometries. Some of them, we may not be able to find smooth geometries. So that's a sort of general set of questions about how to construct pure states from the corresponding to different CFT states, to different pure state geometries corresponding to different CFT states in the Hilbert space. But they're all states very high up in the Hilbert space because they have energies which are quite large in units of CFT. I'll mention one class of states that's interesting, which I won't get time to discuss, which is states whose energies scale with some power of C effective. In fact, in n equals 4 super Young Mills, there are states with energies of order n, not n squared, and these are D-brane states. Okay, but again, they don't change the geometry because their energy is too little to modify the geometry. But they're qualitatively different from the graviton states because now these are like the baryonic states, like these are like determinant operators in the field theory. They're not single trace operators. Did I answer your question, Zhengli? Great. So this is nice, but I want to sort of talk about one class of geometries that certainly are reasonably agnostic to what operators I'm turning on and turning off, and they're sort of reasonably democratic across operators. So I'll just study the state corresponding to the thermal density operator, which is the trace, and try to compute the thermal partition function trace e to the minus beta h. Well, for that, you can imagine doing exactly what I was trying to do before. You create a state in the far past from some boundary operator. You create a state in the far future, the corresponding conjugate state in the far future, and then you identify them to take the trace. Of course, you have to weight them by after doing a Euclidean evolution by e to the minus beta h. So I'll take this identification in Euclidean time with periodicity beta. So the thermal trace can be.
Just to make sure I'm getting the correct picture, that cylinder, that's all in the boundary. So that's purely CFT.
Thank you. Yes, it's purely in the CFT.
Okay, thank you.
Perfect, thank you. And indeed, the thermal partition sum, since I'm identifying the Euclidean time circle with period beta, is studying the field theory on the thermal on a compact circle, and I'll still work in global AdS. So this will be the spatial geometry. And its size, I remind you, is of an order LADS. So there are now two length scales. One is the period of the time circle, and the other is the LADS. So the answer may depend on some ratio of scales between these two guys. And I'll re-summarize the general discussion that I had before, is that I'm trying to compute the CFT partition function with prescribed boundary data for boundary metric and some other boundary operators. I really should be doing a bulk path integral over metric and other bulk fields in the full string theory in the limit of taking lambda very large, some effective coupling very large. I should be doing this by computing the path integral over classical gravitational solutions, but just gravitational solutions. But if I take C effective also large, I can compute this by saddle point in the larger limit, the large C effective. And we may have multiple saddles, and then we should take solutions with least action with prescribed boundary conditions. And again, the condition, if you're at least truncating to saddle point approximation of this string path integral, then we may want to enforce that the solutions we get are smooth gravitational solutions. Okay, this is another place where I'm going to input this condition of smoothness to see what to isolate my saddles. So let's look at what happens to a conformal field theory on a circle cross d-1 sphere. Turns out there are two different saddles. Okay. It's easy to say how to think about the saddles topologically. You can either take the circle and fill it in so that in the bulk you get a disk times a sphere topologically, or you could fill in the disk and get a ball times a circle. So either the circle or the sphere contracts to 0 size in the bulk. The thermal AdS is the one where the sphere contracts to 0 size in the bulk, and the metric is basically the Euclidean metric is just in both cases it's static spherically symmetric, and the thermal AdS metric just has is the AdS metric with Euclidean time identified with period beta. For the Euclidean Schwarzschild AdS, I get a metric which is the Schwarzschild black hole metric with a weak rotation, and I parameterize it in terms of a one parameter family of solutions where R plus is the location of the horizon. We can compute from the solution, from the black hole solution, the Hawking temperature, or in this case, the inverse Hawking temperature, and that is given by this expression, which I'll try to draw for you. And if I draw the Hawking temperature, you'll see that it sort of is a two-lobed function with the temperature blowing up both at small r plus and large r plus. And the transition happens at some critical size, r plus star, which is proportional to d-2 over 2 over d LADS. I think this factor is actually correct. So I'm normalizing, so I shouldn't put divide this. What is a dividing line? The dividing line, so R plus is a length scale. It's the horizon size of the black hole. But we have black holes in AdS, and the AdS itself comes with their own length scale. So we could measure the relative size of the black hole in AdS units, and it's either smaller or larger than the AdS units. And the two features of this graph, the two sides of this function, the fact that it's not monotonic, can be traced back to precisely the fact that if the black hole is small, if it's small on size of AdS scale, then it behaves very much like in flat space because it doesn't see the AdS radius of curvature, and it has a temperature that grows as the black hole gets smaller, exactly like Schwarzschild black holes do in flat space. The opposite limit is a lot more interesting because the opposite limit has no flat space counterpart. The opposite limit is one where the black hole is really macroscopic on the AdS size, is getting bigger and bigger, and its temperature scales with the black hole size. In fact, asymptotically, it scales linearly with black hole size, as I'll show you in a minute. One can compute the entropy of the solution, because this is a thermal solution, just by the Bekenstein-Hawking area formula. And that I've written out, it's proportional to the horizon size to the d-1. I've just written it out in terms of the central charge units, writing the volume of the SD-1. And we can also compute the free energy difference between these two solutions, between the thermal AdS solution and the Euclidean Schwarzschild AdS black hole solution. And you see that for large black holes, for R plus bigger than LADS, the free energy difference is negative. The large black holes dominate. The thermal ensemble.
Good, 5 minutes.
Yeah, 5 minutes. Thank you. So below LADS, we have order 1 free energy. And above LADS, we have order C effective free energy. Because the thermal ADS geometry actually has 0 free energy, it's just the ADS geometry with an identification. The on-shell action is 0 after removing countertops. It's like the vacuum solution with just an identification. There's no interesting answer there. You can compute this either by computing the difference, but if you actually want to compute the exact value of the free energy, you need this full action. At least you need these 3 terms. Because there's a piece from here which cancels a piece from here and a piece from here, which are the divergent pieces, and the finite answer is buried under all of them. Okay. What does this tell us? This tells us that at high temperatures or large black holes, we really have a well-defined canonical ensemble with non-trivial free energy, but there's a phase transition to a sort of phase where there's very little free energy at low temperatures. The order parameter is just the free energy in units of central charge. It's either 0 or 1 in those units. And somewhat very remarkably, you see the same behavior in the free Yang-Mills theory, in the free n equals 4 sup Yang-Mills theory. Okay, so I'll explain these equations in a while, but let me try to draw for you first the phase diagram of n equals 4 sup Yang-Mills that has been conjectured from analysis at 2 extreme points. In free sup Yang-Mills theory, there's a phase transition between a confined phase and a deconfined phase. At an order 1 temperature in units of this sphere size. It's known that this phase transition splits up into a first order phase transition and a third order phase transition at non-zero perturbative coupling. At 0 coupling, the two transitions merge. The conjecture is that this first order phase transition connects up to the phase transition I showed you between thermal AdS and the large black hole at strong coupling, whereas this third order phase transition connects up to the other phase transition that there exists, but one which is at much, much higher temperatures, which is the Hagedorn transition. This happens at T proportional to 1 over root lambda. Yeah, it happens at the temperature of order alpha prime, and so this happens at root lambda. Lambda is large. Perhaps lambda to the 1/4. We're just talking about temperature. So this is conjectural, but what is known is this window here and this window here. And my equations here, which I will explain if people want to know once I stop, has to do with computing the free Yang-Mills partition function. Good. I'll just say one word about what happens in the very large black hole limit and then stop. If you take the black hole to be much larger than AdS scale, then we can decompactify the spherical global black hole to a planar black hole with flat space boundary. I've written down the metric here. And you can compute the free energy and the entropy, and they behave precisely like Stefan Boltzmann law for a conformal system. Photons are also scale invariant in 4 dimensions. So this is like a generalized Stefan Boltzmann statement. The fun thing here is that the black hole entropy is 4/3, is 3/4 the free n equals 4 super Yang-Mills entropy. And this, from, as you probably have been seeing in Ashok Sen's lectures, there were incredible success stories in the mid-90s when people were matching black hole entropy calculations with string theory calculations. And this was an outstanding puzzle for a while because people thought that you should just be able to compute this from the D3 brain story and the answer should match. And they were puzzled why there was a missing factor of 4/3. In fact, people went looking to see if there was some error in the computation. And the answer is no, it's just that there is a non-trivial renormalization in a strongly coupled system between the free theory and the strongly coupled theory. So unlike supersymmetric indices, which are protected between weak and strong coupling, the thermal entropy has no reason to be protected. And what is at least consistent is that the strong coupling calculation coming from the black hole is smaller than the free field calculation coming from counting. Okay. So with that, let me stop for the day and take questions and come back tomorrow and amplify on some of these statements and a few other things that I wanted to discuss.
Excellent, thank you. Okay, some questions.
Let me pause to see if people have other questions and then I'll come back to the Schwartzian, Sergio.
You said that you would show us that other slide a little bit more if somebody asked. I'm going to ask. Yeah. Could we talk about that for a second?
Great.
Yeah.
So I'll explain the calculation. It's very easy. It's a very easy calculation to explain.
Okay.
So you're in free n equals 4 super Yang-Mills. Okay. It's a theory with some number of gauge fields, n squared. The adjoint gauge fields. That there's one gauge multiplet. The 6 scalars, and there are 4 wild fermions. They're all in the adjoint of n equals 4. Let's do the following counting. Let's take the scalar. Let's start with the scalars. They're simple. The free scalars. We are studying this thermodynamics on S1 cross S3. Right? We are studying this on finite volume. So I can Kaluza-Klein harmonically decompose all my fields on the S3. So it's really quantum mechanics now. Okay. So I just have to look at energies of all the states and just count. Compute a quantum mechanical partition function. But it's a very good way to do the counting. So let's think of how to do the counting. For the scalars, the scalar has dimension 1. X has dimension 1. So that's the X here. But then you can think of dx that has dimension 2. And my parameter x is just e to the minus beta. So this is the energy of a single scalar state. And this is the energy of the derivative of the scalar.
Okay.
Okay. So if I'm just writing partition sums, I would write, if I write Boltzmann sum, I would write 1 times the scalar plus 1 times the derivative for the single scalar. When I go to del squared x, second order, I can hit with the derivative. That will have dimension 3. But not all states with del squared acting on it are independent because it's an equation of motion.
Sure.
So I'm removing equation of motion terms.
Okay.
Okay. So you write down the various things, you write it, and then you sort of sum over, and this thing exponentiates. This thing has a Taylor expansion, and you get the higher order terms, and I've moved things around to get this right. So, or other words, maybe the right way to say it is that this denominator factor for scalars is coming from, after removing constraints, is simply coming from hitting with 1 over 1 over 1 minus x is the derivative counting to all orders. It
Okay.
just gives you del plus del squared plus del cube plus del to the fourth for every
Resums.
direction.
Yeah. Okay.
That's for a single scalar operator. Those are all the single operators that you can build from a scalar and derivatives. Same counting for gauge fields, except that now there's gauge constraint, so that's why there's a minus 2x cubed.
Okay.
Similar counting for fermions, except their starting point is with a dimension 3/2.
Sure. Okay.
So that gives me these three functions, these two functions. I've added the bosonic functions and the fermionic functions separately. I've written them separately. Because it's a quantum field theory, it's not a quantum mechanical system.
Right.
So I just did the Hilbert space counting, so now I have to Fock space this Hilbert space. So I have to multi-particle the states. But bosons multi-particle by symmetrization and fermions multi-particle by anti-symmetrization.
Right.
Okay. But you see, the symmetrization and anti-symmetrization is just this exponentiation of these guys with some factors. I think I'm missing a factor of 1 over m here. I'll double check. Okay. That's a bit fast because really what I have to do is I have to keep a track of gauge indices, because these are not really gauge invariant. They're transforming in adjoint.
Mm-hmm.
So what is left is a group character coming from the adjoint.
Okay.
And this group character is this guy. And since I have a group character, I have to integrate over the group. This is the Haar measure on the SUN group. So this is really a matrix model.
Okay.
On the SUN group, coming from the fact. I mean, a physical way to say it is that once you do the Kaluza-Klein reduction, all the modes are massive, except one mode, which is the Wilson loop operator along the S1, the so-called Polyakov loop operator. And that is the holonomy field U. And this is the effective action for the holonomy field.
Okay.
And what is happening in the space transition? So you can just, once I write this down and give you this expression, you can just try to evaluate this matrix model partition function in saddle point. And my statement of the phase transition is that there's a saddle point here where U has 0 wave, which is the where U has non-zero wave, so it's a confined phase.
Mm-hmm.
And the saddle point up here where U has 0 wave, so it's a deconfined phase.
Okay.
And the free energy changes character between here and here. It also jumps from order 1 to order n squared.
This is great, because I was actually going to ask, like, what does confined and deconfined here mean?
Yeah. So confined and deconfined in this language is just that there's nothing to confine because it's a conformal system,
Right.
but there's a scale coming from the S3.
Okay.
And what is really confined and deconfined is the free energies are whether they're order 1 or order n squared.
Okay. Thank you.
I have a couple of quick questions.
Go ahead.
The first one is, where does, maybe you already said that, but where does the expectation that n equals 4 entropy in the free limit is equal to 4/3 of the black hole entropy comes from?
So this is not an expectation, this is an answer. The free answer you can just compute because it's free, it's just free field theory. It's just theory of six adjoint scalars, 1 vector, and 4 Weil fermions. So that computation is straightforward. The n squared comes from the fact that the n squared species. Scale invariant tells you t cubed times volume. The question is, what is the coefficient? The free field calculation tells you the coefficient is whatever, 2/3 pi squared. The black hole calculation tells you it's pi squared over 2. They're both calculations, they're both independent calculations. So maybe I'll just say that this is computed from.
Perfect, thank you.
Can I ask a question?
Mm-hmm.
When you were considering further excited states, you just changed the geometry. But for example, for the thermal state, it's very clear that you take Euclidean on both sides, and you periodically identify the timeline coordinate. My question is, when you are thinking of Lorentzian signature, what is the data that you need to give to the CFT to give you the initial conditions to solve the initial valid problem? Because it's clear that you need the boundary conditions and where they appear, but I'm not clear where the data from the initial conditions appear.
So in the bulk, I don't know how to okay. So what Joao is saying is the following. So if you try to set up the boundary initial value problem, then we are doing something like this. If you're drawing a cylinder, we are setting up some initial conditions here at some t equals 0 slice, and we have boundary conditions specified here. Think of evolving in a box, and then we want to evolve this data forward. Now, this initial data, let's say whatever you give me satisfies constraint equations, bulk constraint equations. That will come with some set of fall-offs for all the fields. So there'll be some fall-offs going this way. Okay, let's just imagine this thing is compactified. So this is really a cylinder. Okay. Now from these fall-offs, we can try to read off webs. But of course, one needs to be normalizable unless we're turning on sources. We can of course turn on sources as well. Then there have to be relevant operators. Otherwise, if they're irrelevant sources, they would blow up on the boundary. But given these fall-offs, we could try to read off and then say, in the field theory, at this instant of time, I'm trying to prepare some state, which I don't know in detail, but at least know what some waves are. Because remember, in a Lorentzian field theory, the Hilbert space only exists at a moment of time. So this initial data is tantamount to picking some state in the Hilbert space. The boundary conditions is tantamount to telling me what the subsequent evolution of the data is going to be, what a Hamiltonian is. Whether you're turning on other sources, whether you're exciting other things as you go along.
Okay, so, but, and so when we specify the initial data, because we have some differential equations, we are specifying the solution with the boundary conditions. And what you're saying is that the initial data is specifying what is the initial conditions for the CFT Hamiltonian evolution as well.
Correct.
Okay.
Correct.
Would we need to do, if we're doing the calculations with those boson stars or anything like that, would we need this kind of setup?
Well, for the boson stars, things are a bit simple because the boson star was a static geometry, so it's time independent. So I mean, the easy things to do are time independent stuff. It's almost like an energy. It's an energy eigenstate of the Hamiltonian. So time dependence is pretty simple in that case. It's all in the scalar oscillations.
Okay.
But indeed, if you want to, I mean, people certainly have studied problems where you sort of set up some initial data here, and you watch collapse happen in AdS, and so on and so forth. So those kind of problems you can solve.
Okay, thank you.
Okay, then go ahead, Samuel.
Oh, hey. Yeah, maybe this is a dumb question. So when you're discussing the entropy of the black hole, are you talking about a black hole in AdS or the entropy of a black deep brain solution? In which context are they relevant?
Good. So in this discussion, I had already taken the near horizon limit and I had talked about the black hole in AdS. This is a Euclidean big rotation of the usual Schwarzschild AdS black hole in global coordinates. This also is the weak rotation. This is the Lorentzian planar black hole in AdS with boundary, which is Minkowski space. This solution can be obtained from the black 3 brane. I don't know how to obtain the previous solution from the black 3 brane for the same reason. I don't know how to obtain global coordinates from the black 3 brane. But the planar black hole from black 3 brane is very simple, because the 10-dimensional solution for the black T3 brane is where H is the same function I had before. It just puts this f of r in these places. So
Okay, I
now if
see.
you take the near horizon limit, this one goes away. This one goes away, but this one survives because, and you get exactly this metric. That was the puzzle.
Well, okay, so if I summarize, and please correct me if I'm wrong. If you take pure AdS and you craft the thermal state, it is a black hole at the center of AdS. And then if you take your string theory solution, which is a stack of D3 rain, then the thermal state is black D3 rains.
Yes.
Okay, thank you.
Yes. Yes. So Sergey, you want to know if I can derive the Schwartzian derivative piece of CFT2 stress tensor from the bulk transformation? Yes, because the Brown-Hanno analysis tells you that in AdS3, you have a boundary Virasoro algebra with a central charge. Right. So any bulk diffeomorphism that acts as a boundary conformal transformation would transform the state.
So can you basically take the stress tensor from the bulk, do a diffeomorphism in the bulk that asymptotically is a conformal transformation, and you would get distortion?
Well, you won't. Well, so let's say you start with the boundary. So when you say, when you take the stress tensor from the bulk, you mean the Brown-York stress tensor that I described plus counter terms. Yes, yes, you would certainly, that would transform correctly under conformal transformations.
Okay, okay. So you get it directly from just a bulk calculation. You get the Schwartzian transformation of the stress tensor.
Yeah, I mean, it has to do that. It has to behave that way. I mean, for example, if you go back to various discussions like computing thermal entropies, like what Matt Hedrick and Tom Faulkner did, and so on, you already see the part in the answer in from the bulk calculation. So what I want to say is that the boundary stress tensor, if you do a bulk diffeomorphism that acts as a boundary conformal transformation, it changes the conformal frame on the boundary. A CFT stress tensor, once you change the conformal frame, has to transform with a Schwartzian piece. Because it's not, it doesn't transform, it's not invariant under boundary conformal transformations. It transforms anomalously because of the Schwartzian data.
Right, but I guess I want to see if I can derive that rather than use that property of the boundary stress tensor.
Yeah, I think the answer is I'm certainly one. I'm sure that one can derive it. The question is whether I'm just getting confused whether it's sort of trivially derivable or whether it needs a step. But all I'm saying is it has to work that way because of Brown-Hammond. But I'm trying to think of whether it's been sort of the various discussions going back, let's say, to just pure AdS3 gravity. I forget, I mean, it was pointed out in Krasnov's papers from the late 90s or earlier, where you can show the boundary action is just Liouville. If you sort of take AdS3 and show what it is, there's a question of how do you write the boundary action? So just like in AdS2, if you put a finite cutoff, you see the boundary action is a pure Schwarzian action because it's the only dynamical mode is the boundary mode, which has a Schwarzian action. You get a similar action in AdS3, which is the Liouville action, and that has the right anomalous transformation property because the Liouville fit there. I'm pretty sure this is correct, but I can try to find a reference for you where it's done.
Yeah, I mean, that sounds pretty much like a derivation. So.
Yeah. Anything else, folks?
I have a question if you want to take one more.
I can take a lot more. Go ahead.
So earlier this morning, Dr. Elevang taught us about the double copy. And she showed us how you can get a closed string from a double copy of a open string. And you showed us earlier this week how AdS CFT comes from a relationship between closed and open strings. So I'm wondering if there's some connection between AdS CFT and the double copy.
Okay, very interesting question. Short answer is I don't know, but let me say a few things. So in addition to what Henrietta might have told you at the level of amplitudes, there's interesting statement at the level of double copies for solutions. Okay. So you can derive nonlinear solutions to Einstein's equations from corresponding solutions to Yang-Mills equations.
Mm-hmm.
Okay. So the simplest class of examples are solutions which come from which have some algebraic special features in gravity. So Schwarzschild solution, for example, you can get from the solution of a monopole in Maxwell's equations with some suitable dressing. And likewise, the Kerr solution you can get. So you could ask your question by asking, can you think of the, I'm pretty sure there must be some corresponding statement for AdS solutions because they have similar properties, although I'm not recalling off the top of my head if people have worked out double copy relation for AdS stuff.
But double copy,
yes,
isn't double copy like a weak to weak, weak coupling to weak coupling duality, whereas AdS is a weak coupling to strong coupling duality?
Yes.
So that would be quite different physics.
It would be quite different physics, but you might ask whether one can be used to inform the other. So it's a different statement, and I agree that the context in which the statement is used is for typically for flat space scattering amplitudes. But one could imagine that you sort of try to embed that by thinking of flat space limit of AdS correlators or something like that. So I totally agree that it's not, the reason I don't know the answer is that it's not a direct connection. But it might be worth asking the question at the level of solutions directly first, whether you can sort of map solutions back and forth. Let me take this offline and think about it.
Okay.
My zero thought answer is I've never thought about it, so I don't know.
Okay, thank you.
I had a question.
Could we possibly get references for the boson star construction and this D-brane construction you mentioned a few slides ago?
The D-brane construction of states with energies of order n.
Yes.
Yeah, I can put in references for stuff. Yeah, certainly.
Great, thank you.
Yeah, the D-brane states, by the way, have been called various things, but the accepted terminology is giant gravitons, because they're not gravitons that speak. Thought there was another question.
Anindya.
Is the two-sided black hole solution that you're going to talk about at any point?
Tomorrow.
Oh.
I got to the one. I got to the Euclidean black hole, so now I can recall.
Okay, I'll reserve the questions for tomorrow then.
But I will say something about the two-sided black hole tomorrow.
Okay, maybe now it's a.
But tell me your question anyway, so that
Okay.
I will incorporate it.
It's basically the Wick rotation of the two-sided black hole. What do you get when you Wick rotate? So it's related to the recent work on this.
Okay. Well, it depends on which coordinates you rotate. You can either get bubbles of nothing, or you can get.
I mean, I'm just asking about the connected geometry. So if you just Wick rotate the solution, you're supposed to get the double disk. But then, is there a way to see the connected geometry in any sense from the classical theory?
Okay. I think the answer is no, but let me think about it and include that in tomorrow's discussion.
So, by the way, I should say for everyone that, well, actually, let's stop the recording, and so that people